or afternoon, as the case may be. Today, we're going to be continuing our exploration of acids and bases by expanding our definition of what an acid or a base is. Now, as time went on, after Svante Arrhenius's definition, they started to realize that there were things out there that had acidic and basic properties that did not necessarily have in them hydronium ions, hydrogen ions, or hydroxide ions, and maybe did not follow the classic pattern. So they realized they had to expand their definition. So a couple of scientists, one Danish chemist by the name of Johann Bronsted and an English chemist, Thomas Lowry, independently proposed an expanded definition which includes substances that are not dissolved in water, yet which still act as acids or bases. Now, according to them, and they jointly share um, the accolades because they both came up with it independently at the same time. But according to them, and this is a good definition, acids technically donate protons. In other words, they donate a hydrogen ion, okay, hydrogen ion. Whereas a base, all right, and remember, not necessarily to water molecules. In the past, using the previous definition, the last lecture, we said that acids were anything that increase hydronium ion concentration, which means that the acid would donate the ion to a water molecule, thus making an H3O ion. But they found that you don't actually have to do that. For example, in this, HSO4 negative 1. In this case, this is donating an acid. When this ion reacts with a carbonate ion, CO3 2 negative, it donates that hydrogen over to it, thus making the hydrogen carbonate ion, HCO3 negative 1, and a sulfate ion. So you can just see the hydrogen is transferred right on over. Nowhere in this is a hydronium ion. Yet, since it's basically the same type of reaction, the transfer or donation of a proton, then it's considered to be an acid. All right. Now, the substance, the CO3 in this case, since it is accepting the proton, then in this reaction, it is acting as an Bronsted-Lowry base. All right. Another example is with ammonia. Now, ammonia accepts a proton from water to form ammonium ions, NH4 plus 1, and is therefore considered a base. Now, if you notice, at the end product, since the water gave up a hydrogen, it therefore produces an OH negative ion. And therefore, it can even be considered a base under the Arrhenius definition. Now, if you notice, water, in this case, is giving up a hydrogen, which means, according to this definition, it is actually an acid, since anything that gives up a hydrogen is an acid. An amphoteric substance is any molecule or ion that can act as either an acid or a base. If you notice, so anything that can act as either an acid or as a base. The classic example is water. Water can give up a hydrogen in order to act as an acid, thus making OH negative ions, or it can accept a hydrogen and thus become H3O positive and therefore act as a base. All right. Now, the next section, we're going to be talking about the strengths of an acid, all right, and a base. Now, a strong acid or base is a specific technical definition. an acid or a base that completely dissociates in aqueous solution. In other words, the dissociation reaction goes to completion. It goes all the way. It's a one-way arrow. For example, here you have a generic acid that reacts with water. You notice it's a one-way arrow, thus producing hydronium ions and whatever the anion is that goes with it. Here's an example of, oops, there it is. Here's an example of a sodium hydroxide that dissolves in water. Again, a one-way arrow to produce sodium ions and hydroxide ions. Now, both of these are strong acids and bases. Now, when you're worrying about numbers and the concentration, the molarity concentration of the hydronium ion will be equal to that of the strong acid. So if you have a 2 molar solution of strong acid, then you have a 2 molar concentration of hydronium ion. The same thing goes if it's a strong base, with a small twist to it. Basically, if it's something like NaOH, you notice it has 1 hydroxide. Therefore, whatever its concentration is, when it dissociates for every 1 NaOH, it's going to produce 1 OH negative. Therefore, the two concentrations are always going to be equal to each other. But if you have something like barium hydroxide, BaOH with a 2, if you notice that for every 1 barium hydroxide, okay, it's going to produce 2 OHs. All right. So if the barium hydroxide has a concentration of 2 molar, since there's going to be 2 hydroxides, we take that 2 molar and multiply it by 2, and thus get 4 molar concentration of hydroxide. It all depends on how many OHs there are. If you have something like aluminum hydroxide, AlOH3, since it has 3 hydroxides, it's going to produce 3 OHs. And therefore, if you have a 2 molar concentration of that, you multiply that by 3 and you get a 6 molar concentration of OH negative. But otherwise, it works just like a strong acid. All right? Since it disassociates completely, it's a very simple way of calculating those concentrations. Now, some common strong acids and bases are as follows. A lot of these you may have heard of, like sulfuric acid, which is found in car batteries, hydrochloric acid, which is in stomach acid, nitric acid, perchloric acid. All of these are strong acids. Strong bases, these guys tend to be, they have OH right there in them usually, and they're usually OH attached to anything in any element in the first 2 columns. Like Na is in column 1, so NaOH, that's a strong acid. If you notice calcium hydroxide, CaOH2, calcium's in column 2, and therefore it is also a strong base. Just so you know, the names of those 2 columns, if you recollect, column 1 were known as the alkali metals, and column 2 were the alkaline earth metals. Well, the term alkali means basic, right? Alkali, basic, those are synonymous. So those elements are actually named because they produce strong bases when paired with OH. Now, basically, these are things that you will just have to know based upon experience. We know sulfuric is a strong acid because it has strong acid tendencies. There's nothing in the name, there's nothing in the formula that just will tell you, hey, look, this is a strong acid. All right. And I'm sorry about that. But I'm not going to make you look at something and say, hey, is this a strong acid or a strong base? Except you can always tell when you look at the chemical reaction, the equation for the chemical reaction. If it is a one-way arrow, that's your clue. Hey, look, that's a strong acid or a strong base. Now, this is as opposed to weak acids and bases. All right? A weak acid or base is one that does not dissociate completely, and therefore it forms an equilibrium reaction. All right. For example, you have a strong base here, a strong acid here, a weak acid, a weak acid, Hb, and it reacts with water and it produces hydronium and an ion B negative. But if you notice, in the middle, it's a two-way arrow. It's an equilibrium arrow. Therefore, this is an equilibrium reaction, and therefore it is a weak acid. Now, if you look at the difference, maybe graphically, if you have, before you dissociate, you have that much strong acid, and boom, after dissociation, you have no more strong acid. All of it has gone and become hydronium ions and the anions. But with a weak acid, if you notice, you have, before it dissolves in water, you have a certain amount, and then you still have a lot of that same acid in solution, and it's only dissociated slightly to form some hydronium and some ions. Now, the strength of an acid only depends, or base, only depends upon the degree to which it dissociates. All right? Strong acids and bases dissociate completely. Weak acids and bases dissociate incompletely, i.e., they reach equilibrium. Now, strength is different from concentration. People learning chemistry often get those two confused. They think they mean the same thing. They don't. You can have a dilute strong acid, or you can have a concentrated weak acid. All right. And they do not have really anything to do with each other. It's simply the degree to which it disassociates. Now, of course, since this is an equilibrium equation, and since we are going to have to worry about figuring out concentrations of things, there is a KEQ equation that is designed specifically for acids and bases. Now, we're just going to focus on the one for acids, though there is one for weak bases too. We're not going to worry about it in this class. But it is known as the acid ionization constant, or K subscript A. All right, Ka. Now, this is the equilibrium constant, the KEQ, for a reaction in which a weak acid disassociates by donating a proton to water. And it always follows the same pattern, okay? It always follows the same pattern. You have acid, whatever the acid is, and it reacts with water. And it's going to form in equilibrium a hydronium ion and an anion, both of which are going to be in aqueous solution. All right. Notice the acid is also in aqueous solution. So when we want to write out the Ka, or the KEQ expression, remember it is the concentrations of the products times each other divided by the concentrations of the reactants times themselves. But since water is always a liquid, you never include it. So the Ka is always going to be this right here, where hydronium ion concentration times the anion concentration divided by the concentration of the acid. Now, since acids each time only lose one hydrogen at a time, therefore the coefficients are always going to be ones. You're not going to have to worry about balancing these equations. It's always going to be a 1-to-1-to-1 ratio. And therefore, there's no exponents in the Ka. And since all of the hydronium ion came from the acid at the same time as the anion, those two are always going to be equal to each other. So whatever the concentration of hydronium is, it's going to be equal to the concentration of the anion. Now I have a sample problem that I wish to show you, so we will get going with that. Right. So we have a sample problem here for a Ka problem. Now, in this case, the question reads, if Ka is equal to 1.6 times 10 to the negative 6, and the concentration of the acetic acid is 0.23 molar, what is the hydronium ion concentration in the following equation? And here we have the balanced chemical equation. Remember, for acids, it's always going to be a 1 to 1 to 1 to 1 ratio. So the first step is we have to write out the Ka expression. So we have Ka, just like KQ, it's products over reactants. So this is an AQ, so I'm going to take the concentration of hydronium and then multiplied by the concentration of acetate, which is this ion here. And then I have the reactant, the acetic acid itself, COOH. All right. And I do not include the water because it is a liquid, and you never include solids or liquids in any KEQ problem. Now, in this case, I have the Ka and I have the acid concentrations, and I'm trying to find the hydronium ion concentration. So I'm trying to find this guy. Now, if you remember, since these guys dissociate, it's a 1-to-1 ratio, the concentration of hydronium is going to be equal to the concentration of the acetate ion. So what I'm going to do is since I'm solving for those, I'm going to pull a trick from algebra, and I'm going to say, all right, this is what I'm solving for. I'm going to make that x, just as a placeholder. All right. And since if that's x, that means that is x as well, right? They're equal to each other. So therefore, that's x. Now I have numbers for here and here. So when I plug them in, I see that I have 1.6 times 10 to the negative 6 is equal to x times x, which is x squared, over the concentration on the bottom, which is 0.23 molar. Now I want to solve for this, right? So I'm going to multiply. I have to get rid of the 0.23, so I'm going to multiply both sides by 0.23. 0.23. So I'm going to multiply those. Those are going to cancel out. And then those two times each other will give me x squared. I want to find just x, so I'm going to multiply those two together and then square root both sides. All right. So on my handy dandy calculator, I'm going to go and I have, let's clear that, 0.23 times 1.6 negative 6. I'm going to push equals, all right? And now I want to square root that. So basically, I go to the little square root button here, second square root my answer. So I go second again. Down on the bottom, I have where it says answer. So I do that. I square root my answer and I push enter. And that is my final answer. This is going to be equal to x. And if you notice, I have two significant figures there and 2 there. So I want to round this off to only 2 digits. So I have x, which is, remember, the concentration of H3O. That is going to be equal to 6.1 times 10 to the negative 4. And it's a concentration, not a Ka, so the units are M. And that's my answer. Okay. So problems that ask for, they give you the Ka and ask for these, you do it like this. Some of the problems will give you the concentrations of all three of these and ask for the Ka. Well, those are simple. You just plug it into the expression, multiply, then divide, and you get the Ka. But that's how you do a typical Ka problem.